Hi, in this video, we're going to go over the solutions to Worksheet 7.6. So first up, here we go. So we got a baseball, it's 140 grams. Quick comment, we just want to catch that right away. We don't want things in grams, so that would be 0.14 kilograms. It's traveling at 30 meters per second. It moves the fielder's glove backwards 35 centimeters. That to be in meters, so divide by 100, divide by 1,000 on the to change the grams into kilograms, divide by 100 to change the centimeters into meters. 1,000 grams in a kilogram, 100 centimeters in a meter. Okay, so let's says first up, draw an energy bar graph diagram. So we'll just sketch one of those real quick. Gravitational energy and elastic energy. Middle bit here. Kinetic energy, gravitational energy, and elastic energy. Okay, so we're going to start out with kinetic energy because the ball is moving. The ball in the system, and then it is caught, and all that energy leaves. So to glove or fielder. You can to the glove or to the fielder, however you want to do that. But there you go. That's your energy bar diagram. It says what was the average force exerted by the ball on the glove? To do that, we're going to just write ourselves the energy equation. Energy equation would say kinetic energy minus the work to the glove is equal to 0 because we have no energy left, right? Nothing in that final bar graph there. So that's going to be 1/2 mv squared minus, because we are looking for the force, we're going to change that to L x. And so that's going to be 1/2 the mass, 0.14 times by the velocity, 30, minus F. It went delta x, which was 0.35. So let's go ahead and do the calculation. 0.5 times by 0.14 times by 30 squared. And give you 63 minus 0.35. See, we can add that to the other side. So we'll do, and then divide by 0.35, and you get the F to 180 newtons. It's a force, not an energy, so that would be in newtons this time. All right. Next one, a 60-kilogram student jumps off the 10-meter platform into the pool. So it doesn't actually give us a spot there, so we're gonna just draw because we're supposed to draw an LOL graph for each one here. So we'll do that real quick here. We got energy, gravitational energy, elastic energy. Circle there. Let's see here, we'll put the student in the system. And they start out with gravitational energy because they're up there on that platform, right? Ask yourself, are they moving fast? Are they up high? Do they have a spring? So, and then if you kind of read through the rest of the problem, it says how much kinetic energy do they possess at impact? So that would mean that at the end, it's all elastic energy. So we're not losing any energy anywhere. It doesn't talk about that. So first step would be to calculate the gravitational energy. So gravitational energy is just mgh. So 60 times by 9.8 times by 10. So that tells us that the student starts with 5,880 joules of energy. How much kinetic energy does she possess at impact? So because she didn't lose any energy. She has 5,880 joules of kinetic energy at impact. What was her velocity? So to do that, you can just divide by 30. That gives us 196 v squared square root. And so the square root of 196 v is equal to 14 meters per second. It says repeat for a 75 kilogram diver. You're going to end up with exactly the same answers. So just your gravitational energy is 75 9 times by 10. So you're going to get 75 times 10. Oops. So obviously we get more gravitational energy. But when you take that and put it into the kinetic energy for kinetic energy, equals 1/2 times by 5 squared. And I'm just going to go through and do all the here. Oh, look, 196 equals v squared, v equals 14 meters per second. So you get the same answer. And that's because ultimately the m's are going to cancel. So it's not, your velocity at the bottom does not depend on your mass. So also makes sense because we could have solved this using kinematics instead of energy, and we know that in kinematics, right, the Paul-John-Ringo equations, there's no m in anywhere in there, so the velocity doesn't depend on the mass. So, right, meaning we could have solved it that way. So, a spring whose spring constant is 850 newtons per meter is compressed 0.4 meters. What is the maximum speed it can give to a 0.5 kilogram ball? So again, we're supposed to draw an energy bar graph for each one of these things. So start that off here. So it's a ball. Had to be in the spring. Oh, let me finish doing this. Sorry. So we start out with elastic energy. So that means we have the spring in the system and the ball in the system. Well, those are the two things that are kind of giving us energy there. We're going to start out with elastic energy. Doesn't talk anything about gaining or losing energy throughout this whole process. And so that's going to leave us with kinetic energy at the end. So moving along, right, using this to write our equation, that's going to tell us that elastic energy is equal to kinetic energy. So that's going to give us 1/2 k x squared is equal to 1/2 mv squared, 1/2 times by 850 newtons per meter, press 0.4 meters, 1/2 0.5 v squared. All right, there you go. 16.5, what you should get. Moving along to the next one. So a child descends a 0.5 meter high slide and reaches the ground with a speed of 20.8 meters per second. Compare his initial and final energies. How much energy was dissipated due to friction while sliding? So in this case, we don't draw the energy bar diagram until B. So I'm going to go ahead and complete A. So his initial energy is gravitational energy, is mgh. So that's going to give us 24 times by 9.8 times by 5 meters. So the child starts with 24 times by 9.8 times by 5. And then, so that's the initial energy. Final energy is kinetic energy. Point 0.5 times by 24 times by 2.8 squared is going to give you 94. Joules. Okay, so let's take a look at this, right? If we compare these two numbers here, so how much energy was dissipated due to friction and sliding? Well, we started out with 1,176 joules of energy. We ended with that amount. So how much, so then let's say, sorry, let's do this differently. We started out with 1,176 joules worth of energy. We lost some energy to friction, and we ended with 94.1 joules, right? So doing a little rearranging, subtract or add the work from friction to the right side of the equation, subtract the 94 over there, you're going to get that we lost 1,176 minus 94.1 work due to friction is going to be, we lost 1,082. I'm just going to do some rounding there, joules worth of energy. So that was how much we lost. So draw a quantitatively accurate LOL graph. It doesn't need to be super quantitatively accurate, but let's see here. So let's see here. Things that we should put in the system. Mostly just the child. put the child in there. Child starts out with gravitational energy. I probably could have done a better job of that. But, starts out with gravitational energy. Loses most of it, right? So I'm going to put 3 out of 4 of them as being energy lost to friction. So I suppose that's where the quantitatively accurate is, meaning that we lose most of the energy, because right, we lose out of the 1,000, 1,100 that we start with, almost 1,200 that we start with, we lose most of that. We lose 1,000 of it. We end up with only 94 of it. So we lose most of that energy. Hence the 3 coming out and 1 left. So there you go. Moving on to number 5. So a child pulls a 5.6 kilogram sled at a distance of 12 meters along a horizontal surface at a constant speed. The force of friction is 9.15 newtons, and the cord has a tension of 12.9, makes it a 45-degree angle to the horizontal. How much work is done by friction? So, force of friction, work is equal to force times by distance. So, um, right, work due to friction would be equal to the force of friction, 9.15 newtons, times by the distance you pull, which would be 12 meters. And that would be 1,009.8 joules. Not too hard there. Moving on to the next one. How does this compare to the amount of work done by the child? So to figure out the child, we gotta do a little bit more work here because we can still use the work if you force time by delta. But let's recall that the force is only the force that is parallel to the displacement. So, right, if we kind of picture pulling a sled. So if we kind of picture this, we got a child, they're pulling a sled. Let's see here, I can do a little bit better than that. And right, they're pulling in that direction, which makes a 45-degree angle. And so let's recall that they're pulling in that direction, so that's delta x direction. And so we want only the part that is parallel to the displacement. So that means, so the displacement is to the left. I want this 12.9 cosine of 45 degrees. That's the part that is going to be relevant to us. That's the part that actually adds energy to the system, so it does work, versus the 12.9 sine of 45 does not do any work. It doesn't add any energy to it. So because remember, in this force right here is the force that is parallel to my delta x, meaning since my delta x is horizontally to the left, as drawn, then I want the force that is horizontally to the left. So I didn't have to do anything up here because this 9.5 is horizontally to the right, so it's already horizontal. So I didn't need to do that. And of course, because it's to the right as opposed to the left, it would be, it would be negative. So as we take a look at this, we see that we would go 12.9 cosine of 45 times by the delta x, 12 meters, and 12.9 times by cosine 45 degrees times by 12 is going to give you 109.5 joules. So explain why this makes sense. So this makes sense because, right, the sled is moving at a constant speed. So all the energy put in by the child is lost to friction, right? Because it's not getting added to kinetic energy. If it was, it would be going faster. So okay, number 6. A boat pulls a water ski. Oh shoot, sorry, hang on. A Number 6, a boat pulls a water skier. The water skier rides to the side of the wake so that the rope pulling her makes a angle theta with the direction the boat is traveling. If the tension in the rope is 75 newtons and the boat does 350 joules or 3,500 joules of work while driving 50 meters, what is the angle theta? I think one of the tricky parts of this is find the picture. So here's our boat. Grab you both. Try that again. Um, there we go. Less crappy. Okay, boat is traveling forwards, right? So that's just the direction the boat's going. Our water skier is over here, and so the rope goes that way. That's 75 newtons. Okay. The angle theta is this angle right here relative to the direction the boat is going. And so there we go, basically. That's kind of the drawing. So the skiers, as I drew it over to the right, the boat is going straight up, and the rope is going to make that angle right there. So how do we figure this out? So we can get back to our, hey, there we go. Work is equal to force times by distance. Again, where the force is the part that is parallel to the direction of motion. So we are told that the amount of work done by the boat is 3,500 joules. The force is 75 cosine theta because I want only, oops, go green. I want only that part, right? Not so not the sine part because the sine part is perpendicular to the direction of motion. So that's the force that I want, and we pull 50 meters, so that's the delta x there. So let's note that the only thing we don't know is theta there. So to solve this, we can take remember with multiplication, it doesn't matter the order in which we do it. So we can take the 75 and multiply by 50. So 75 times by 50 is going to give us 3,750 Newton, or sorry, I guess I don't know what the units are. I guess they would, yeah. So it'd be joules, but it doesn't really matter. Again, we're trying to find theta, so you got to get theta all by itself. So you're going to divide by the 3,750. So it's going to give you 3,500 divided by 3,750, and that gives you on this side 0.93 is equal to, on this side, the only thing we have is cosine of theta. So to get theta all by itself, you have to inverse cosine both sides. That's going to undo the cosine. And so what you're going to be left with is equal to theta, right? Because when you inverse cosine the cosine, it's going to end up being all by itself. And so then you just put that into your calculator. That's a button, right? Inverse cosine of 0.93. and you are going to get 21.6. So theta equals 21.6 degrees. We'll make sure your calculator's in degrees, not radians. Okay, moving along to number 7, which is a little bit tricky here. So you have to get a 500 kilogram piano into the second floor of a building that's 3 meters tall. How much work does it take to lift a piano straight up to a height? Well, right, work is equal to energy. You're changing your gravitational energy. Gravitational energy. So final gravitational energy minus initial gravitational energy, 0. So that would be 500 times by 9.8 times by 3 meters minus the 0 that we started with. So we do 14,700 joules worth of energy. All right. Next one is tricky. So how much work does it take to push it up a frictionless ramp as indicated below? So never mind how difficult it is to push something up a frictionless ramp is just a joke, right? If it's frictionless, it'd be very difficult. You couldn't do it, right? Because you have nothing to push against. That's the only reason it's there. So the hardest part here, so we're going to end up using work is equal to force, the force that you push times by the distance of the ramp. So here's the thing. Right now, we don't know either of those things. So we're going to have to figure out the length of the ramp. So let's start there. To figure out the length of the ramp, it says use the Pythagorean theorem. So that's just 18 squared plus 3 squared to, Pythagorean theorem is usually a squared plus b squared equals c squared. Without going into all of the details here, 18 squared plus 3 squared. That's going to give you 333, square root that, and you're going to get 18.2. So 2 meters. So 18.2 meters. Okay. We also need to know the angle. So in order to find the angle, it says use inverse tangent. You could actually use any of them, but tangent theta is equal to opposite over adjacent. So that would be 3 over 18. So tangent both sides. Should have done that differently. You'll see what's going on here. Sorry that it's taking me a little while here. I did things out of order. So here I have tangent theta equal to 3 over 18. That's just going to leave me with theta is equal to 1 of 3 over 18. So try that out. We got inverse tangent of 3 divided by 18. That's going to give me 9.5. 9.5 degrees. All right, so that's part of it. You'll see why we need the angle here in just a second. So we've gotten the delta x part. Now we got to get the F push part. So let's first, it says, think back to how we did inclined planes. You might need to actually take your physics journal and go back to the inclined plane notes. But let's take a look at what we got here. We have the force of gravity. Just draw a quick force diagram here. We got our force of gravity. We got our normal force, that direction. We have the forced push, which is what we're looking for there. And so let's recall that how we do these is we break them, the force of gravity, into pieces. And that part's going to become mg sine theta. So what ends up happening is, right, this force and this force have to be the same because it's moving at a constant speed. So that means F push has to equal mg sine theta, right? Because moving at a constant speed. So balance forces. So going back to here, we have work is equal to mg sine theta times by the delta x, which we know. So plug in all the numbers. So the mass is 500 kilograms, 9.8 sine of 9.5 degrees times by 18.2 meters. So now to multiply all that together, 500 times by 9.8 times by the sine of 9.5 times by 18.2. We get that the amount of work done is 14,719 joules. So why does this make sense? So it's roughly the same amount. Like, sure, it is 19 joules more, but it makes sense because that these two numbers are basically the same, right? 20 joules doesn't really make any difference when we're talking about 14,000, you know? And so both of these numbers are roughly the same. So why does it make sense that they're the same? Well, we've accomplished the same task, right? Because we didn't lose any energy to anything, it makes sense that both of those numbers are going to be the same. So um, let's do this. Right? So because we accomplished the same task, so work is equal to your change in energy, which is the same in both cases. and we didn't lose energy in either case. Didn't lose energy in either case. Ah, so there you go. And right, the difference of 20, like the reason that this is 14,700 and this is 14,718, the reason that it's off by that much is just, right, we ended up doing a lot of rounding and a lot of calculating in part B. And so as a result, like there's those rounding, they just ended up making it, off by enough. That's where the 20 came from. So like if we had not rounded like at all, these two numbers should be exactly the same. So we should have ended up with 14,700 here. But because we had to round, we rounded the angle, we rounded the length, we rounded the force. Like we did lots of rounding. I guess we only really rounded the angle and the length, but because we rounded those two numbers, that's why it ended up being off. So, all right. Well, that was a long one. Thank you very much for watching. As always, if you have any questions, let me know. And thank you very much.